Hi everyone. So again, I'm going to take some stuff out of the How to Think Like a Mathematician, and we're going to go over some things that some of it is review, but a lot of it's going to be very new information. Okay, so I'm very excited. So I love mod stuff, like the mod n and all those things. So if you would like a quick review of that, let's say, for example, we have some x mod n. Well, n is a non-zero, well, no, it's a natural number. That covers non-zero. So it's a natural number, and so x is going to be equivalent to x plus any k times n mod n, where k is just any integer. So that's a very brief overview. So basically n is kind of like a zero, but when we do math inside of here, it might be special things and you wouldn't consider it as zero. Okay, but when it comes to mod land, it is zero. So it's like you're adding zero, but in a tricky way. Okay, so I mean, they're recalling something from a previous example that you can go to in your book. Remember, you have access to your book on D2L. That this is an equivalence relation for any natural number n. So very interesting. Okay, so, and from this other example, they also have the equivalence classes, which are these, which actually is a very interesting trick that you will want to know for exams and things and homeworks and stuff, is that when you're working mod n with equivalencies, often your guess will be 0 through n minus 1. Or you can think about 1 through n. Okay? Because what you're thinking about is you're going to be using the division lemma most likely, and you're going to be looking at your remainders. But any remainders bigger than n minus 1 don't really make any sense, unless it's n, because you're also considering it as 0. But if you want to learn more about that, you can go back to my old videos, and I go very in depth with that. Okay, so excellent. This set of equivalence classes is denoted by z sub n. Okay, so typically how people think about z sub n, and so now we're breaching into territory of things that you won't need to know for the exam. So z sub n, people define as 0, 1, all the way up to n minus 1. Okay, where the relationship is everything is modulo n. So addition mod n. And so is multiplication. So remember, when I did teach you mod before, I said we're only really doing addition in this class. I said, but you could look into multiplication because it is fun, or at least I think it's fun. So we're going to kind of go over it today, a little bit of it. Okay? All right, so how you can think about this is, it's like the integers mod n. Okay, that's kind of what this set is. But usually we call it just zn. Okay? So now we can define arithmetic on the classes by the following. Okay? So now we're back to talking about these equivalence classes. Okay? So the equivalence class of x plus the equivalence class of y is going to actually be the same as the equivalence class of whatever x plus y is. Similarly with multiplication. And so why I want to take this screenshot from your book is they have a great visual here. So note that what we are doing is defining arithmetic on the set of equivalence classes, not on the set of integers. We are saying that we multiply the equivalence classes x and y by defining the product to be the equivalence class of x times y. Okay, so here z7 is 1, 2, 3, 4, 5, 6, 7. Or maybe we should have added 0 in the front. I like that better. And that's typically how people do it. Okay. So 3 times 5. Well, that's going to be equal to 3 times 5, which is equivalence class of 15. Well, 15 mod 7 is 1, because we can minus 14 from it. Okay? So let's think about who's in our equivalence class of 3. Well, this is going to be all the elements x in x mod z, such that x twiddles. So this is just all integers. Wait, no. This is all elements. Sorry. 3 plus 7 times n, such that n is an integer. Okay, and so that's how each of these are defined. And that's why they're all distinct, because none of them can be each other under this circumstance. Okay, 3 minus 7, which is negative 4. We could do that times 5. And we hopefully will get the same equivalence class as before. Okay, so we'll get, let's see, negative 20. Okay, negative 20 mod 7. Oh, well that is 1, because 7 times 3 is 21. Okay, cool. So, of course we can't do proof by example, but this is kind of what I'm saying of like, we're multiplying the classes together and we should still get the same equivalence class. So this example up here, they're bringing up a concern. So we don't want this to happen. Since x twiddles z, we would like it that x times y is the same equivalence class as z times y, since this means that the equivalence class of x equals the equivalence class of z. Okay, so we would really like that to happen. And I just showed you an example where that does happen, but remember we can't do proof by example. Okay, so they also give an example of adding two things. Adding we're probably a lot less concerned about because we know how to add in mod. Okay, so we're good with that. So they really start talking about it. They do a discussion. I don't want to go too deep into it. And they also give a proof and a theorem of what I was just talking about. You can look into it. It's on, let's see, do I have page numbers? I don't. Let me check. It looks like it's on page 239 in your textbook if you would like to look at it, or you can look at it right here. So this is best done with primes. So if we have z sub p, where p is prime, another way that mathematicians also often call this is the field over p. And so you don't need to know all of this, so that's fine. But all that means is that every element has an inverse when p is prime. When we're over a p prime. Okay, so let's consider. Let's consider z sub 5 maybe. Okay, so we have 0, 1, 2, 3, 4. And let's try to figure out who's going to be whose inverse. And what the heck does that even mean, to be something's inverse? So if we have an n in some zp, then n inverse is also in zp, such that n times n inverse is equivalent to 1 mod p. And so remember, p is prime. So we can do this with things that aren't primes, but we're just not always guaranteed very pretty like inverses and such. prime I just think is a nice way to introduce you to these ideas. Okay, so that's in general. Yeah, sorry, any non. So let's start with 1. Well, 1 is its own inverse mod 5. How about 2? Ooh, okay. Well, so let's think about it. So it's going to be some element in here. So it could be, so 2 inverse could be, well, not 0. 1, 2, 3, or 4. Well, 1's not going to work because 2 times 1 is 2, mod 5. 2 is not going to work because that's going to be 4. Ooh, 3 is going to work because 2 times 3 is 6, and so that's 1 mod 5. And lastly, 4 wouldn't work because that would be 3 mod 5. Oh, sorry. I should write it this way. The inverse of 2 is equivalent to 3 mod 5. And that looks so weird, doesn't it? Isn't that crazy? So if you wanted, yeah, I don't know. This stuff really hypes me up. Okay, so the inverse of 3, you guessed it, that's going to be 2. Okay, so now how about the inverse of 4? Well, it's going to look like it's going to be 4, because that's all we have left. So 1, no. 2, no. 3, okay, we have 12, that would be 2 mod 5, no. Ooh, yeah, because 16 is 1 mod 5. Awesome. Oops. Oh, yeah. No, that's right. Okay, awesome. So now, why in the heck is this useful, Danica? Well, we love being able to do inverses of stuff. So like, let's say we're trying to show that 3 is equivalent to, 8 mod 5, and pretend that this isn't very simple. Remember, I like to show simple examples so you can build up. Okay, so let's say I want to get rid of that 3. I want to get 1 on one side. And that can be useful for a lot of reasons that has to do with number theory and stuff. I could go on all day. Okay, so then we have multiply both sides by the inverse of 3. Which is allowed. We can multiply both sides by the inverse of 3. But we're in mod 5 land. So this one does go to 1, but what we actually have is this is actually 2. How crazy is that? And we know that that's true. I don't know. I just think that this stuff is totally awesome. But yeah, you can do this other places as well. You can also do it with non-prime. So let's try Z4. 0, 1, 2, 3. Okay, so there wouldn't be a way for us to write it as an FP because 4 is not prime, as you know. Okay, so let's say inverse of 1 is going to be 1 mod 4. How about, do we have an inverse of 2? No, we don't. And so how we know that is, so we go through all of them. So, well, 2 times 2, that's going to be 0. 2 times 3, that's going to be 2 mod 4. Okay, so no, there exists no 2 inverse in Z4. Okay, so then how about an inverse for 3? Do we have one of those? Well, it would have to be 3, so let's see, 3 times 3, that would be 9. 1 more than 8. All right, yes, that is true. That is its own inverse. Okay. And so, oh my gosh, it would be so exciting to talk to you about why primes are so special like this. You probably noticed something special about 2 is it's a divisor of 4. But I could go on all day, and you know that primes don't have any divisors besides 1, which is always its own inverse, and itself, which is the additive identity. So we don't consider the inverse of the additive identity. Okay, hope you have a great week. Bye.